Hello, my friends. We will begin our next video tutorials, and our playlist will be called Beginning of Algebra. Let's begin. Like us and subscribe, and let's get started. Today we are going to learn an absolute number, an absolute value of any real number. As you see from this picture, assume we have any number A, which is real number. As I already mentioned, this symbol in mathematics called it denotes any. So this is denotion for any number A. This symbol means in any number in the set of real numbers. For any number A, which is real, we have this denotion, absolute value of number A. As I know, very often young mathematicians, when they have this notion, it's quite hard to realize what does it mean and how to work with this object. I will give a definition which is very easy. Let's write definition. Absolute value denoted as A, absolute value of A, of any real number, A, is a distance to zero. This is the main idea. So absolute value of any number A is just distance to zero. And that's why if we have here number A, positive number A, for example, 5, distance to zero will be 5. And if here minus A is, for example, minus 5, then distance to zero again will be 5. So without any confusion, absolute value is distance, and this is always positive. That's why let's give an examples. For example, absolute value of number 5 is 5, and the absolute value of number minus 5, because distance from number minus 5 in the real line to 0 is again 5. It's always positive. And for example, minus 8.5, absolute value of this is 8.5. Minus 2 and 1 over 3, an absolute value of this 2 and 1 over 3. An absolute value of 8 and 5, 8.5, is again 8.5. That's why an absolute value of minus 8.5 and absolute value of 8.5 are equal. For example, if we have an absolute value of 4 plus 2 minus 7, since 4 plus 2 is 6 and 6 minus 7 is minus 1, it will be absolute value of minus 1, which is 1. And if we give general definition, which you already encountered in different books, we write first, if number A from the real line or any real number, if number A is positive, or we write A is positive or equal to 0, not negative, then absolute value of A is A, and we already gave examples. And next, if A, real number A, is negative, or A is less than 0, then A, this is already negative number. For example, it can be, if A is minus 2, then absolute value of minus 2 is 2. And 2 is minus 2. We will learn it in next video tutorial, but anyway. So this is minus A. Interesting. For example, absolute value of minus 4 is 4. We just have to put, instead of A, minus 4. A is minus 4, and in this case minus A will be minus 4, which is 4. Or we have another definition which is more technical and often used in mathematics. We will use more symbols of mathematics in mathematics, more symbols of mathematics, because after these tutorials on arithmetic and algebra, we will move on and we will learn linear algebra, higher algebra, and so on. And it's very important to be able to use these symbols. A general definition is absolute value of A is equal to, this is the symbol for cases. We have different cases. So absolute value of A is equal to A if A is more than 0 or equal to 0. And this is minus A if A is less than 0. So this is a general definition, and you now know what is absolute value of any number. Like us and subscribe, and thank you very much for your attention. See you in the next tutorial. In this tutorial, we will learn laws of exponents. Like us and subscribe, and let's get started. First of all, the first law of exponent is the power of the product of factors is equal to the product of powers of each separate factors. For example, assume we have 2 times 3 times 4 times, say, 77, and this all is to the power of 5, then this power of multiplication is a multiplication of powers, it will be 2 to the power of 5 times 3 to the power of 5 times 4 to the power of 5 and time 77 to the power of 5. A general formula is written as, say we have numbers a times b times c times and so on. We assume that a, b, and c are numbers, and this is to the power of n. In this case, this is equal to a to the power of n times b to the power of n times c to the power of n times and so on. This is a general formula, and let's assume one more example. Assume we have x minus a times x plus b times x minus c, and this everything to the power of 3. In this case, these 3 factors and using previous rule, we will have x minus ra to the power of 3 times x plus b to the power of 3 times x minus c to the power of 3. This was first rule, and of course a reverse is also valid. For example, first of all, let's rewrite this formula. We can reverse this formula and write that a to the power of n times b to the power of n, c to the power of n, and so on. This is equal to a times b times c times and so on to the power of n. This is the same formula, but we changed the places, changed right place and left place. And example will be, assume we have 1 over 3 to the power of 5 times 2 over 7 to the power of 5 times 4 over 9 to the power of 5. In this case, we can combine factors and have 1 over 3 times 2 over 7 times 4 over 9, and this everything to the power of 5. And we used this previous formula. Let's give the next rule. It was rule number 1. Next, rule number 2 will be a divided by b to the power of n. This is a to the power of n divided by b to the power of n. Or the power of a fraction is equal to the fraction obtained by dividing the same power of dividend by the same power of divisor. This is the main formula, and a reverse of this formula is also true. Let's give examples. First example, assume we have 4 over 5 to the power of 3. This will be 4 to the power of 3 divided by 5 to the power of 3. Or 2 over 3 to the power of 4 is equal to 2 to the power 4 times 3 to the power 4, which is 16 over 81. Another example, assume we have a plus x divided by b plus x, and this everything to the power of 5. Using previous formula, this is a plus x to the power of 5 over b plus x to the power of 5. Let's use another formula. This is the same formula, but inverse version of this formula. A to the power of n divided by b to the power of n. This is a over b to the power of n. Using this formula, we can solve an example. Assume we have 4 over 5 to power 5 times 3 over 8 to the power of 5. And this will be, using our formula, this will be 4 over 5 times 3 over 8, and this everything to the power of 5. We can perform cancellations here. This will be 1, and here we will have 2, and this is 3 over 5 times 2, or 10 to the power 5. Next law or rule for exponent, rule number 3, is when multiplying powers with the same base, add exponents. Assume we multiply powers with the same base. In this case, a and a are the same, so the base is the same. In this case, we just add exponents. So a to the power m times a to the power n will be a to the power m plus n. We just add exponents. For example, 2 to the power 3 times 2 to the power 2 will be 2 to the power 3 plus 2, which is 2 to the power 5, or 32. Another example, x plus b to the power 3 times just x plus b. In this case, it will be equal to x plus b, and power will be 3 plus 1, or x plus b to the power 4. Next law, law number 4, is in dividing powers having the same base, subtract the exponents. Assume we have a to the power m divided by a to the power n. This will be a to the power m minus n. So when we had multiplication, we add, and when we had division, we have to subtract. And this is the main formula. Examples are, assume we have 7 to the power 5 divided by 7 to the power 3. Or in other form, this will be 7 to the power 5 over 7 to the power 3. This is equal, using previous formula, to 7 to the power 5 minus 3, or 7 to the power 2, 7 squared, which is 49. Another example, x plus y to the power 3 divided by x plus y to the power 2. In other form, it will be x plus y to the power 3 over x plus y to the power 2. This is x plus y to the power 3 minus 2, or This is just x plus y to the power 1, which is just x plus y. And next law, law number 5, is when we have power of a power, multiply exponents. So a to the power m, and this is to the power n, this is just equal to a to the power m times n. Examples are, this is a law, and examples are 2 to the power 3, and this everything to the power 2. In this case, we have to write 2 and multiply exponents. This will be 3 times 2, or 2 to the power 6, which is 64. Next example, assume we have a to the power 2, a squared, times b to the power 3, divided by 3 to the power 4. And this everything to the power 3. So in this case, we have a to the power 2 times 3 times b, we can write dot, or we can avoid it, b to the power 3 times 3 divided by c to the power 4 times 3, or this is a to the power 6 times b to the power 9 divided by c to the power 12. Next example, next law number 6, any number to the power 0 is equal to 1. It can be, for example, 999 to the power 0 is 1, 2 over 3 to the power of 0 is 1, and so on. Next law, law number 7, is a to the power minus n is equal to 1 divided by a to the power n. This is actually can be shown. Let's prove it. And we will use previous laws in this case. This symbol means we begin the proof of this result. So since we have a to the power n times a to the power minus n, using previous rules, previous laws, this will be a to the power n minus n, which is a to the power 0, which is 1. Or we have a to the power n times a to the power minus n is equal to 1. Now we divide both sides of our equation by a to the power minus n, and we have a to the power n is equal to 1 divided by a to the power minus n. So we have a proof of this result. And let's give an examples for this law. For example, 2 to the power minus 3 is equal to 1 over 2 to the power 3, or 1 over 8. 3 to the power minus 2 is equal to 1 over 3 to the power 2, or 1 over 9. We have in particular a result that a over b to the power minus n will be b over a to the power n. So we write a positive, we change the sign of our exponent, but we have to interchange numerator and denominator. Let's prove this result. It's quite easy. Let's begin our proof. A over b to the power minus n, using previous result, is a divided by a over b to the power n, which is equal to, using previous laws, a to the power n divided by b to the power n, which is equal to, by definition, this is equal by definition, or we write equal by definition, 1 divided by a to the power n over b to the power n. Using, we can transform division into multiplication. Watch our arithmetic playlist. And 1 can be written as 1 over 1. So this is 1 or 1 over 1 times b to the power n times divided by a to the power n, or just b to the power n divided by a to the power n. Using previous laws, this is b divided by a to the power n to the power n. So we have a result, and if we rewrite it, we have a result here. So this formula can be used, for example, if we have an example 2 over 3, and this is to the power minus 2, is equal to 3 over 2 to the power 2. Or this is equal to 3 squared, which is 9, divided by 2 squared, which is 4. Thank you for your attention. It was everything for this tutorial. Like us and subscribe, and have a great day. In this tutorial, we will learn negative and positive numbers operations. After this tutorial, we will be able formally explain and solve any, for example, addition, subtraction, and multiplication or division with negative and positive numbers. Like us and subscribe, and let's get started. First of all, we have to remember definition of absolute number, of absolute value, sorry. Assume we have a and its absolute value. By definition, if you don't know this, please watch our previous tutorial on absolute value. This is a if a is bigger or equal to 0, and this is minus a if a is less than 0. For example, minus 5, absolute value of minus 5 is 5, and absolute value of 5 is 5. So this is always positive. Let's first of all talk about addition. Addition of numbers with different signs. To add two numbers with different signs, we have to formally to follow certain rules. Assume we have like signs. So we have plus, for example, 7, and this is plus 7, plus positive 7, plus 7. Since signs are the same, the rule is to combine absolute values. We combine absolute values and prefix a common sign, which is plus, and this will be plus 14. If we have, for example, minus 7 plus minus 4, in this case, signs are same. In this case, the rule is we have to combine absolute values. So this is absolute value of minus 7 plus absolute value of minus 4, and we assign common sign, which is minus. So since this is 7 and this is 4, answer will be minus 11. This is formal rule on how to perform addition. For example, assume we have minus 2 plus minus 7. In this case, it will be the common sign minus and the sum of absolute values. Absolute value of minus 2 plus absolute value of minus 7, which is minus 9. What if signs are unlike? This is the second case. In this case, for example, we have minus 7 plus 2. So signs are unlike. We perform addition, but signs are unlike. In this case, the rule is find the difference between absolute values and prefix the sign of the number with greater absolute value. Of course, minus 7 has greater absolute value, which is 7, and the sign of it's minus 7 is minus. So we assign the sign of number with greater absolute value and calculate difference of absolute values. Difference is 5 because we have minus 7 minus absolute value of 2 plus 2. This is absolute value of minus 7 is 7 and absolute value of plus 2 is 2, and this is minus 5. Another example, 4 plus minus 6. So we have addition, and here the signs, since we also have here plus, signs are different and addition is performed once again. We assign, we prefix sign of the number with bigger absolute value, which is minus 6, so this is minus, and difference of absolute values will be 2 because this is absolute value of minus 6 minus absolute value of plus 4. This is 6 and this is 4. 6 minus 4 is 2, and answer will be minus 2. Of course, this is formal approach, and we can use logic to calculate these examples. For example, the first example, this example can be done as minus 7 plus 2 can be written as, since minus 7 can be written as minus 5 minus 2. We write minus 5 minus 2 plus 2. And this, we have a cancellation here, and answer will be minus 5. Another example, this example can be done as 4 plus minus 6 can be written as, since minus 6 is minus 2 minus 4, we write this as minus 2 minus 4, and our 4 will be plus 4. So we have cancellations here, and answer will be minus 2. What about subtraction? Any subtraction of numbers with any signs can be transformed into addition. For example, 7 minus 7 can be written as 7 plus 3, which is 10. And for example, minus 4 minus 2, or let's assume plus 2, can be written as minus 4 plus minus 2. And this example, as we did before, can be written as minus 4 minus 2, which is minus 6, using previous examples. Next, let's talk about multiplication. Multiplication of numbers with different signs. We have a very famous table. If we have plus times plus is equal to plus, plus times minus is equal to minus, minus times plus is equal to minus, and minus times minus is equal to plus. So the common rule is that if we have different signs, for example, assume this is rule number 1, 2, 3, and 4. If we have plus 2 times plus 3, in this case, we just multiply values, absolute values of 2 and 3. This will be 6, and sign will be plus times plus is plus. So this is first example. Second, if we have plus 2 times minus 3, absolute value of plus 2 and minus 3 is 2 and 3. We perform multiplication of absolute values. It will be 6. And then, since plus times minus is minus, we have minus 6. And minus 2 times plus 3 is again minus 6. And minus 2 times minus 3, minus times minus gives plus, so it will be realization of fourth rule. The pattern here is that when we have different signs, this is always minus. Plus times minus is minus, and minus times plus is minus. So when signs are different, multiplication gives always minus. And when signs are the same, it can be plus times plus is plus, and minus times minus is again plus. So the second rule, when we have same signs, multiplication always gives plus. And second rule is when we have the multiplication of different signs, sign always will be negative. Let's solve several examples, several easy examples. For example, we have minus 3 times minus 5. Minus and minus gives plus. It will be plus, and multiplication of absolute values. Minus 3 times minus 5. This is 3 and this is 5. So answer will be plus 15. Plus 1 over 3 times plus 2 times minus 6 times minus 7. Plus multiplied by plus gives plus. Plus multiplied by minus gives minus, and minus multiplied by minus gives plus. So answer will be with the sign plus, and we just now assume only absolute values which are always positive and multiply absolute values. So 1 over 3 times 2 times 6 times 7. What we have cancellation here, 3 and 6, and we have 2 here. So this will be 2 times 2 times 7, which is 28. So answer will be plus 28. Next example is assume we have minus 1 over 4 times minus 3 times 8 plus 8 and times 2 over 3 with the sign minus. Again here, minus times minus gives plus, plus times plus gives plus, and again plus times minus gives us a minus. So answer will be with minus, and we just look at absolute values of these numbers. So we have 1 over 4 times 3 times 8 times 2 over 3. Let's now perform cancellations. We have 8 and 4 are cancelled. We have 2 here, and this 3 and 3 are cancelled. So we have 2 times 2, which is 4. And answer will be minus 4. What about division? Division is the same as we know from arithmetic playlist. If you don't understand this, please watch arithmetic playlist. Very important for understanding arithmetic operations. Division is multiplication actually, but let's look at example. For example, minus 6 divided by plus 2. Since minus 6 is minus 6 over 1, and this can be written as division of fractions, and we can transform division of fractions into multiplication of fractions. It will be, we just have to interchange numerator and denominator here, and this will be, here we have sign minus, and here we have actually plus. So minus times plus is minus, and let's perform cancellations. So it will be minus 3. Another example, assume minus 8 divided by minus 2 divided by 4 plus 4 and multiplied by number minus 3. In this case, we write it as minus 8 times minus 1/2 times plus 1/4 and times minus 3. And again, here we have minus times minus gives plus, and plus times plus gives plus, and plus times minus gives minus. So answer will be with the sign minus. And let's look at absolute values 8, 1/2, 1/4, and 3, and multiply absolute values. It will be 8 times 1/2 times 1/4 times 3. What we have, let's perform cancellations here. 8 is cancelled out with these 2 and 4, and we have minus 3. Next, I want to explain how to multiply numbers with different signs. For example, minus 2. When we multiply this number by brackets, and inside brackets we have some numbers and letters. For example, this is a plus b plus c minus 2d plus 15, for example. In this case, we multiply our number minus 2 by each element of these numbers, by each elements inside brackets. In this case, we have, first we multiply minus 2 by a, it will be minus 2a. Next we multiply 2 by next element, this will be minus 2b. Next we multiply our 2 with third element, this will be minus 2c. Next, multiply with next element, it will be minus and minus gives us plus, and 2 times 2 is 4, 4d. And multiplication with last element gives us minus times plus is minus, and 2 times 15 is 30. Another example, assume we have minus 1/3 times 3a minus 6b minus 9c. In this case, we multiply our minus 1/3 by first element, minus times plus, because here we have plus, gives us minus, and 1/3 times 3 times a. This is minus 1a or minus a. Next we have a minus times minus is plus. So we have plus 103 times 6b. And this will be plus 2b. And next, minus times minus gives us plus 103 times 9c, or multiplied by c. In this case, we have here plus 3c. So answer will be minus a plus 2b plus 3c. And the last example, assume we have two brackets, a minus b. Now the brackets will be minus 3 plus 2c. In this case, we multiply a by first element. Next, we multiply a by the second element. Next, we multiply minus b by the first element and multiply b by the second element. So we have a times minus 3, this is minus 3a. A times plus 2c, this is plus 2ac. Minus b times minus c is plus 3b. Minus b times minus 3 gives us plus 3b. And minus b times plus 2c gives us minus 2bc. It was quite obvious. It was everything for today. Like us and subscribe, and thank you for your attention. In this tutorial, we will learn introduction to polynomials. After this tutorial, we will be able to understand basics of polynomials. Let's get started. First of all, we have to define a monomial. Monomial is, by definition, is a product of factors which are numbers, letter or power of letter. And that's all. So monomial is a product of factors, and each factor is a number, a letter, or power of a letter. Examples of monomials are, for example, 2f. This is a product of number 2 and letter f. It can be a squared and b cubed. So here we have coefficient 1, but we do not write it. So this is a power of two letters, a to the power 2 and b to the power 3. Another example is 3abc. And another example is minus 4 x squared b cubed and y to the power 5. So here we have a number minus 4 and let multiplication of letters. So here we have x to the power 2, b to the power 3, and y to the power 5. Next, we have to, after the concept of monomial, we have to understand the concept of coefficient. Coefficient of monomial. Coefficient of monomial. So here, the coefficient can be any factor of the monomial. For example, for monomial 2f, we can say that 2 is a coefficient, so we have 2 of f, 2 times f. This is f plus f, 2 times. Or we can say that f is a coefficient, and in this case we have 2 plus 2 plus so on plus 2, and we have this addition of number 2 f times. So coefficient can be any factor of monomial. For example, another example, assume we have 3abc, and it's better to take a number as a coefficient if you have a numbers. In this case, you have abc plus abc plus abc. So this is abc 3 times, or 3 multiplied to abc, and abc is a times b times c. This is the multiplication of 3 letters. We can also say that, for example, a is a coefficient. In this case, we have that 3abc, this is 3bc plus and so on 3bc, and we have an addition a times. So this was a concept of coefficient of monomial. Next we have to define similar monomials. Similar monomials. Monomials are similar if they are same or differ only in a coefficients. For example, a monomial 2abc and 99abc are similar because they are same, but coefficients are different. And we can, for example, add these two same monomials. In other words, we have 2 of abc plus 99 of abc. All in all, we have 101 of abc's. Another example is minus 4 x squared b cubed and y to the power 5, and another monomial 6 x squared b cubed and y to the power 5 are similar because coefficients differ, but they are same because another part of our monomials are the same, and we can add these two similar monomials. For example, minus 4 of this monomial x squared b cubed y to the power of 5 plus 6 of this monomial will be minus 4 plus 6 is 2 of these monomials. So similar monomials can be added and subtracted. We could write here, for example, minus, in this case, minus 4 minus 6 would be minus 10. Minus 10. So if you want to add and subtract monomials, only similar monomials can be added and subtracted. Another example is, for example, we have two monomials, a times x squared, y cubed, z and t to the power of 5, and another monomial is b x squared, y cubed, and z and times t to the power of 5. So obviously these two monomials are similar because this part of monomials, these parts are the same, but if we assume that a and b are coefficients, we can add these two monomials. So we have a of this monomial plus b of this monomial. And this is a plus b times this monomial, x squared times y cubed times z times t to the power 5. Often we can avoid writing these dots which represent multiplication. Anyway, we can write it, we can avoid writing it. Another example is, let's finish with addition of similar monomials and talk about addition. Addition of monomials in general. Assume we have 3x to the power 2 times y to the power 2 minus 5x to the power 2 times y to the power 2 and plus 6x to the power 2 times y to the power 2. Three of these monomials are the same, and the coefficients, only coefficients differ. So we have 3 of monomial minus 5 of monomials plus 6 of monomials. So 3 minus 5 is minus 2. Minus 2 plus 6 is 4. And answer will be 4 times x to the power 2 times y to the power 2. It was example number 1. Another example is a times x to the power 2 times y squared minus b x squared y squared plus c x squared y squared. In this case, we can assume that a, b, and c, a minus b and c are coefficients, and another part of our monomials are same. So we can add these monomials, and coefficients will be a minus b plus c is just a minus b plus c of times of monomial x squared y squared. Another example, assume we have sum of monomials 4x cubed y squared minus 3x squared y squared minus 2x cubed y squared plus 6x squared y squared plus 5x and y. So let's add the monomials which are similar. This monomial 4x cubed and y squared is similar to this monomial. That's why we write 4 minus 2 is 2 of x cubed and y squared. Next, this monomial and this monomial are similar. That's why we write minus 3 plus 6 is plus 3 of x squared and y squared. Next, this monomial is not similar to any monomial. That's why we have to just rewrite last monomial, and we have plus 5xy. And that's all. So we have 3 monomials, and these monomials are not similar, so we cannot add. And this is the final answer after simplification of our monomials. Next, let's talk about taking a common factor, and we will give examples of taking a common factor. For example, we have a sum of monomials a x squared y cubed plus b x squared y cubed plus c x squared and y cubed. In this case, we can take a common factor from these monomials, and here x is entered into first monomial with the power 2, and here also x is entered with the power 2, and here we have also with the power 2. So we can take out x squared. And what about y? Y here is entered with the power 3, here also with the power 3, and here also. So we can take out y with the power 3, and we will have, for first monomial, this is a times x squared and y cubed plus b plus c. So we took common factors from these 3 monomials. Another example is, assume we have 2ab squared plus ab squared, and of course this monomial can be written also as ab cubed, because these 2 factors of monomial can be multiplied, and b times b squared is b cubed, plus d ab cubed, ab squared. It's easy to see that these monomials are similar, and of course, obviously, ab squared is a common factor for these three monomials, so we can take out a common factor a b squared, and we have 2 for first monomial plus b for second monomial and plus d for third monomial. And this last monomial can be written also if we change factors. This can be written as this. Next, let's define a concept of polynomial. Polynomial. A polynomial is just a sum of any number of monomials. And for example, 4a squared minus 2b minus 2x squared and y squared is a polynomial because this is a sum of three monomials. And as I said, by definition, polynomial is a sum, or by sum we mean plus or minus of any number of monomials. And if we add several polynomials, we will have again a polynomial. For example, let's add this polynomial, a sum of monomials, add to different polynomial minus 12a squared minus c and plus 7b minus 2x squared and y squared. And let's rewrite our polynomial without brackets. The first part will be the same. And this minus will affect the second monomial, and we will have minus 12a squared, minus and minus is plus c. Next, the third monomial is plus 7b minus 2x squared y squared. Next, we just perform addition of similar monomials. It's easy to see that first monomial is similar to this monomial, and next second monomial 2b is similar to this monomial, and this monomial is similar to this monomial, and we have to just add these similar monomials. For the first one, for red monomials, it will be 4 minus 12, which is minus 8a squared. For green monomial, it will be 2b plus 7b is plus 9b. And for yellow monomial, it will be minus 2, and minus 2 is minus 4x squared and y squared. And do not forget this monomial. This monomial doesn't have any similar monomials, and that's why we just rewrite it. So this will be a final answer after simplification of our monomial, of our sum of several monomials. Next, let's talk about multiplication of monomials. Multiplication of monomials. Multiplication of monomials. When multiplying monomials, exponents of appropriate letters are combined and numerical coefficients are multiplied. Let's give examples. examples. Example number 1. Let's multiply two monomial 2ab squared times minus 3ab cubed c. And in this case, as I already defined, when we multiply two monomials, numerical coefficients are multiplied. So this coefficient and this coefficient, we have a multiplication of two coefficients. 2 times minus 3 is minus 6. Minus 6. And then exponents of appropriate letters are combined. For example, this a and this a times a is a squared, and this b and this b squared times b cubed is b to the power 5, and our c is, we just rewrite it, it will be just c. So we have a multiplication of two monomials. Another example is, example number 2 is 7 over 3 x times y to the power 3 z times 3 over 21 xy z squared. So first we multiply coefficients of these monomials, and it will be 7. Let's write it. Here. So 7 over 3 times 3 over 21. This is the multiplication of coefficients. And of course, this will be, since we have here a cancellation, and here will be 3. This is 1 over 3. And x times x is x squared. Y cubed times y is y to the power 4. And z times z squared is z cubed. So the final answer is 1 over 3 x squared y to the power 4 and z cubed. Next and last thing I want to talk for this tutorial is a division of monomials. Division of monomials. A quotient or result of division of two monomials can be simplified if dividend and divisor contain certain powers of the same letters. Let's give examples. First example, assume we divide 12x to the power 3 x cubed times y squared times z, and this is divided by 3x squared y and z. And this division can be represented as a fraction. And as I defined division of monomials, if dividend and divisor contain certain powers of the same letters, we perform a division. Of course, coefficients are divided, so 12 divided by 3 is 4. X cubed divided by x squared is x to the power 3 minus 2 times y. We have here y to the power 2 divided by y is y to the power 2 minus 1. And we have z to the power 1 minus 1. And here, of course, this is 3 to the power 3 minus 2. 3 to the power 1, or sorry, x to the power 1, which is x. This is y to the power 1, which is y. And this is z to the power 0, which is 1. And final answer will be 4 x, y, and z to the power 0 is 1. So we avoid writing 1. This is the final answer. Another example of division of monomials is second example, 28 x squared times a b cubed divided by 4 x b cubed. In this case, 28 times 4, 28 divided by 4 is 7. X squared divided by x is just x, and a is written, we rewrite a, and b to the power 3 divided by b to the power 3 is b to the power 0, which is 1. And we do not write 1. So this is a final answer of our division. Another example is the same example, but assume we have a little bit, a little difference. Assume in the denominator of our quotient, of our fraction, we have not 4x b cubed, but 4x and times b to the power 5. In this case, we have 7x a, and b will be 3, or let's write it as, here we will have b squared, because this b to the power 3 is cancelled, and from this b to the power 5 we are left with b squared, and this can be written as 7xa and b to the power minus 2. It was everything for this tutorial. Like us and subscribe. Thank you very much for your attention. In this video tutorial, we will learn multiplication of polynomials. Like us and subscribe, and let's get started. Product of two or more polynomials is equal to the sum of products of each terms. For example, assume we have ax plus b. This is a polynomial which contains in itself two monomial. Watch previous tutorials. Assume this polynomial is multiplied by another polynomial, cx plus d. In this case, how multiplication is done? First of all, we multiply first element of the first polynomial we multiply by the first element of the second polynomial, and then by the second element of the second polynomial. Next, we multiply b, second element, by first and second element of second polynomial. So we have 4 multiplications. Let's perform these multiplications. Ax times cx will be, let's write it, ax times cx. This will be ac x to the power 2 plus ax times d. Assume a and d are coefficients, and we will write it as ad times x. Next, we multiply b times cx and plus bd. And if we rewrite, it will be acx squared plus adx plus bcx plus bd. Next, we know that these two monomials are similar monomials because we have common elements here, and assume these AD and BC are coefficients. That's why we can add these two monomials, and result will be we can write it as AD plus BC times x. So all in all, this can be written as acx squared plus bd. So our resulting polynomial consists of a monomial with x squared, second monomial with x to the power 1 or just x, and third is actually, we can write here x to the power 0, which is equal to 1. Next example, assume we have a plus b plus c times x. In this case, the second polynomial is just one monomial. If you don't know what is a monomial, watch previous tutorials in Algebra playlist. Next, we multiply, as in the previous example, a, b, and c to x. So we have 3 multiplications, and we have ax plus bx plus cx. And of course, this also can be written as x times a plus b plus c. Let's repeat our main rule. The product of 2 or more polynomials is equal to the sum of products of each terms of this polynomial. Each term is a monomial. Next example is, assume we have 4xy plus 3axy to the power 2, and this polynomial is multiplied by next polynomial minus 2ax to the power 2 plus 5y to the power 3. And let's perform multiplication. Multiply this element, this monomial, by this monomial. It will give us minus 8 a x to the power 3 and y. Next, we multiply this, our first element, by the second element of the second polynomial. It will be 4 times 5 plus 4 times plus 5 will be plus 20. X, we write x. Y times y to the power 3 will be y to the power 4. Minus, next we multiply this element, this monomial, to this monomial, and we will have 3 times minus 2 is minus 6. We have already minus here. minus 6, a times a to the power 2, x times x squared, x to the power 3, and y squared is left. Next, we multiply this element by this element, and it will give us plus 3 times 5, 15, a, x, and y squared times y to the power 3 will be y to the power 5. And that's all. We performed our multiplication. And last example, more common example, assume we have 3x squared minus 2x plus 5, and this polynomial is multiplied to the second polynomial multiplied by second polynomial 3x plus 4. Result will be 3x squared times 3x will be 9, x to the power 3, plus 3 times 4 is 12, x squared, minus 2x plus minus 2x times 3x will be minus 6x squared, minus 2x times 4 will be minus 8x, plus 5 times 3x is plus 15x, and plus 5 times 4, 20. Next, we observe here, we see that this monomial and this monomial are similar, and we can perform addition and subtraction of these similar monomials. This monomial and this monomial, these monomials are also similar, and let's perform addition. This will be 12 minus 6, 6x squared, and this will be minus 8 plus 15 plus 7x. And if we rewrite, result will be 9x to the power 3 plus 6x squared plus 7x and plus 12, plus 20, sorry. We can also perform this multiplication in a different form. Let's do it. As we already performed our multiplication for decimals, for decimal fractions in our arithmetic playlist. Watch it if you don't know. Let's multiply. Let's take the same example, actually. Multiply this polynomial by this polynomial. And let's write it again. Let's write our multiplication in different form. 3x squared minus 2x plus 5. This polynomial is multiplied by polynomial 3x plus 4. Let's perform this multiplication. First, we multiply the first element of second polynomial by each element of the first polynomial. This, and this. (3x times 3x squared is 9, x to the power 3. 3x times minus 2x is minus 6x squared. 3x times 5 is plus 15x. Next, we multiply this element by each element of this polynomial. 4 times 3x squared is 12. Is 12x squared. 4 times minus 2x is minus 8x, and 4 times plus 5 is plus 20. Next, we perform addition of these two resulting polynomials. It will be 9x to the power 3, minus 6 plus 12 is plus 6x squared, plus 15 minus 8 is plus 7x, and plus 20. So the result of the multiplication of this polynomial and this polynomial will be this polynomial. And you can see that this polynomial is the same as our resulting polynomial here. So we can perform both ways of multiplications. Like us and subscribe, and let's finish our tutorial. Thank you for your attention. Hello, my friends. Today we are going to learn shortcut multiplication of polynomials. At the end of this tutorial, you will be able to reproduce some very important formulas for shortcut multiplication, like this presented here. Following special cases of multiplication of polynomials are frequently encountered and used and should be memorized. First, let's begin with the most important example. Our first example will be a shortcut multiplication of a plus b plus c plus so on e and plus f to the power 2. Shortcut multiplication formula for this will be, we have to take a squared of every element inside brackets. So it will be a squared plus b squared plus c squared plus so on e squared plus f squared. And next we have a double multiplication of each pair of elements inside this bracket. So it will be, first we have to multiply a by every element inside brackets. So it will be 2ab plus 2ac plus so on 2ae and plus 2af. Next we multiply next letter b by each element beginning from c and so on, b multiplied by e and b multiplied by f. And we do not multiply b by letter a because we already have this multiplication here. So take the multiplication of b by every element. It will be plus 2bc plus so on plus 2be and plus 2bf. Next we multiply letter c by every element here, and we multiply by e and f. Let's do it. It will be plus so on plus 2ce and plus 2cf. And at last we take a multiplication of, here we have dots, and we have a multiplication of letter e by f. So it will be plus 2ef. So once again, a plus b plus c and so on plus e plus f to the power 2 will be equal to, we have to take every element inside brackets squared, And then we have a double multiplication of every combination of two unique elements inside brackets. It will be the first formula, very important formula for shortcut multiplication of polynomials. It's very important to understand that instead of these letters can be different things, for example, monomials and even polynomials. So for every element, this formula works. A plus B plus C to the power 2. Once again, using previous formula, this will be equal to A squared plus B squared plus C squared and plus double multiplication of every two different elements inside brackets. It will be 2AB plus 2AC plus 2BC. And if we take, as another example, more simpler formula, A plus B to the power 2, it will be A squared plus B squared plus 2 multiplication of two different elements inside brackets, and it will be just AB. This is famous formula for shortcut multiplication. And another type of how this formula is written is A plus B squared is equal to A squared plus 2AB plus B squared. To prove this formula, we can prove it straightforward. And our previous general formula also can be proved using straightforward calculation. And A plus B to the power 2 will be equal to A plus B times A plus B. And if we perform a multiplication of these two polynomials, it will be A squared plus AB plus AB plus B squared. These two AB's gives us 2AB, so we have A squared plus 2AB plus B squared. And this is the proof of these formulas. And using the same straightforward calculation, we also can prove this our main formula, our main general formula. Next, it's very obvious that instead these letters A, B, C, and so on can be anything. Say it can be monomials. That's why let's assume examples. Example number 1. Let's calculate using previous shortcut multiplication formulas for polynomials. And using these formulas, let's write 2ax plus 3ay to the power 2. And perform this to solve this problem using shortcut multiplication. We take first, let's write it 2ax squared plus 2ax times 3ay plus 3ay squared. And if we write it, it will be 4a squared x squared plus 2 times 2 times 3 will be 12. So it will be 12a squared x and y plus 9a squared y squared. Another example is assume we have 5xy plus 2a to the power 2. So using previous formula, since we have a plus b to the power 2 is a squared plus 2ab plus b squared, it will be 25, which is 5 to the power 2, x squared, y squared, plus 2 times 5 times 2 will be 20, x, y, a, and plus 2a squared will be 4a squared. Next example is how to write a shortcut formula for a minus b squared. And to do this, we can write this as a plus minus b to the power 2. And use our previous formula, it will be a squared plus 2a minus b plus minus b squared. And we know that it will be minus 2ab, and this will be just b squared. So we have a squared minus 2ab plus b squared. And this formula, let's rewrite this formula. It will be a minus b to the power 2, which is a squared minus 2ab plus b squared. This is another formula for shortcut multiplication of polynomials. Using this formula, first of all, let's prove this formula. Along the same way, we can prove this formula using straightforward calculation. So we write a minus b times a minus b. It will be a squared minus ab plus b squared. And these 2 minus ab's gives us minus 2ab. So it will be a squared minus 2ab plus b squared. So we have a proof for our formula. Using this formula, we can write solution for, using this shortcut multiplication formula, we can write a solution for, say, 5x to the power 3 minus 2ya to the power 2. So it will be, this will be a, and this will be b. So a squared is 25 x to the power 6 minus 2ab. So it will be minus 2, 5x to the power 3, and 2ya. And this will be 20 x to the power 3, y, and a. Plus b squared will be 4y squared and a squared. So all in all, it will be 25x to the power 6 minus 20x to the power 3 ya plus 4y squared a squared. Next example, let's write as a next example shortcut multiplication formula for a minus b and minus c using previous formulas. We can write this as a plus minus b plus minus c to the power 2. And using previous general formula, This is equal to a squared plus b squared plus c squared and plus 2a minus b plus 2a minus c plus 2 minus b times minus c, and this gives us, let's rewrite it, a squared plus b squared plus c squared minus 2ab minus 2ac and plus 2bc. Next shortcut formula is written as a minus b times s plus b is equal to a squared minus b squared. To prove this formula, we again use straightforward multiplication. That's why a minus b times a plus b is a times a gives us a squared minus ab minus ab and minus b squared. Here we have plus ab. So we have a cancellation of two ab's, and all in all we have a squared minus b squared. And this is the proof for our shortcut formula, for this formula. It was everything for today. Next time we will prove another shortcut multiplication formulas for polynomials using Hayam Pascal triangle, and that's why we have to first of all understand what is Hayam and Pascal triangle, understand binomial coefficients, and then we will use these to understand some very important shortcut multiplication formulas in algebra. Thank you very much. Like us and subscribe. In this tutorial, we will learn Hayam Pascal triangle and a binomial theorem. At the end of this tutorial, you will be able to reproduce Hayam Pascal triangle and understand what is the common between this triangle and this formula, or how to use Hayam Pascal triangle to write a shortcut multiplication formula for a plus b to the power of n. Like us and subscribe, and let's get started. First of all, we have to explain the concept of definition of factorial. When we write n factorial, what does it mean? By definition, this is equal by definition. So this symbol means equal by definition. This is equal to 1 times 2 times 3 times and so on times n. As an example, 4 factorial is equal to 1 times 2 times 3 times 4. Or if we perform our multiplication, it will be 24. 2 factorial is 1 times 2, which is just 2. 6 factorial is 1 times 2 times 3 times 4 times 5 and times 6. And if we perform multiplication, it will be equal to 520. Next, we have to define this is called, if we write this, This is called 6 choose 2. Let's define this mathematical object and let's give it its abstract definition. If we have n choose k, by definition, this is equal to n factorial divided by k factorial times n minus k factorial. This is the definition of n choose k. Using this definition, we can write that 6 choose 2 is equal to 6 factorial divided by 2 factorial and 6 minus 2 factorial, which is 4 factorial. This is 6 minus 2 factorial is equal to 4 factorial. And if we write this, it will be 6 factorial divided by 2 factorial and 4 factorial. Using the definition, 6 factorial is 1 times 2 times 3 times 4 times 5 and times 6. 2 factorial is 1 times 2 and times 4 factorial is 1 times 2 times 3 times 4. We can perform a cancellation of this 1 times 2 times 3 times 4 by this. And we will have 5 times 6 over 1 times 2. We can delete this and we will have 5 times 3, which is 15. In other words, 6 choose 2 will be equal to 15. One feature of n choose k is that n choose k is actually equal to n choose n minus k. This is frequently used feature of this object. This is very obvious by definition. If we use this definition of n choose k, this is obvious that these two objects have the same definition. Only these two parts in denominator will be changed. So that's why this formula is quite obvious. First of all, let's explain how Hayam Pascal triangle is constructed. To do this, we write the first node for our triangle, and each node of our triangle has two nodes under the parential node. Again, under these nodes, we also have two nodes. So this is like a tree, like a pyramid. Under each node, we write two nodes. Next, we write number 1 at the corner of our pyramid. So that's why we write here 1, and we write 1 at the corner of our pyramid. 1. Next, under how to fill nodes which are empty. For example, what number is written in this node, in this point. We take two previous numbers, just before this node and we take the sum of these two numbers. Because 1 plus 1 is 2, we write here 2. Next, using the same, along the same way, since 1 plus 2 is 3, we write here 3. 2 plus 1 is also 3, so we write here 3. Here we have 1 plus 3 is 4, that's why we write here 4. 3 plus 3 is 6, that's why we write here 6. And 3 plus 1 is 4, and we write here 4. This triangle is infinite triangle, and we can repeat this process infinitely. And this is Hayam Pascal triangle and the way how this triangle is constructed. Next, assume the levels of our triangle. Assume this is level number 0, and this is level number 1. This is level number 2, level number 3, level number 4, and so on. We have infinite number of levels of our triangle. What is important here to note is that this number 1, for example, because this number belongs to level number 4, is equal to 4 choose 0. This number 4 is equal to 4 choose 1. And this is equal to 4 choose 2. 4 choose 2, and this number 4 is equal to 4 choose 3. And this one is equal to 4 choose 4. Along the same line, for example, this 3 is equal to, because we have line number 3, this is equal to 3 choose not 0 but 1, and this is equal to 3 choose 0. For example, this 2 is equal to, because this is line number 2, this is equal to 2 choose 1, and this is equal to 2 choose 0. This is 2 choose 2, and so on. So we have a relationship, something common between the object and choose k and our Hayam Pascal triangle. For example, look at this. 6 is equal to 4 choose 2, and using definition of n choose k, we write, for example, 4 choose 2 is equal to 4 factorial over 2 factorial and 4 minus 2 factorial, which is equal to, again, 2 factorial. If we rewrite it, it will be 4 factorial over 2 factorial and 2 factorial. This is equal to 1 times 2 times 3 times 4 over 1 times 2 times 1 times 2. Let's perform a cancellation of this 1, 2 and this 1, 2. And we have 3 over 4 over 2, which is equal to 3 times 2, which is 6. So our formula, our rule is correct. That's why 4 choose 2 is equal to 6. Along the same line, we can check that what was written here is correct. So now we know what is Hayam-Pascal triangle and what is the common thing between this triangle and the factorial and n choose k. Okay, next let's explain how to write shortcut multiplication formula for this mathematical expression, or how to write a shortcut formula for a plus b to the power n using Hayam-Pascal triangle. I will show it. First of all, let's construct Hayam-Pascal triangle once again. Once again, we write number 1 at the corner of our triangle. And here we write the sum of these two numbers. 1 plus 1 is 2. Here 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So we created Hayam-Pascal triangle. And once again, let's write lines for our triangle. Line number 0, line number 1, line number 2, line number 3, and line number 4. And how to use these lines to write a formula for a plus n to the power n, a plus b to the power n. Let's do it. It's quite easily done. This first line corresponds to a plus b to the power 0. This is just 1. And a plus b to the power 1 is just a plus b. So these two coefficients, a and b, is written here as, a to the power 1 and a to the power 0. And b is written in the opposite way, b to the power 1 and b to the power 0. And that's why this is equal to a plus b, because 1 is not written. A to the power 1 is just a, and b to the power 0 is 1. So this is equal to a plus b. Next, if we write a plus b to the power 2, we take the first element of our expression and write it here in our triangle in next way. We write a to the power 2, a to the power 1, and a to the power 0. And element b is written in opposite way. This is b to the power 2, b to the power 1, and b to the power 0. And it will be the formula for our shortcut multiplication. This is equal to a to the power 2, a squared, plus 2ab plus b squared. Next, a plus b to the power 3. To write shortcut formula for this expression, we again use line number 3 of our triangle and write element a as a to the power 3, a to the power 2, a to the power 1 and a to the power 0, and write our b in opposite way, b to the power 3, b to the power 2, and b to the power 1, and b to the power 0. And this will be formula for our shortcut multiplication. If we rewrite it, it will be a to the power 3, a cubed, plus 3a squared b plus 3ab squared plus b cubed, and so on. Let's again here write shortcut formula for a plus b to the power 4. It will be along the same way. We take our first element and write it here along the line number 4 as a to the power 4, a to the power 3, a to the power 2, a to the power 1, and a to the power 0. And b is written as b to the power 4, b to the power 3, b to the power 2, b to the power 1, and b to the power 0. And this will be formula for a plus b to the power 4. If we rewrite it, it will be a to the power 4 plus 4, a to the power 3, b plus 6, a to the power 2, b to the power 2, plus 4a, b to the power 3, plus b to the power 4, and so on. We can use our Hayam Pascal triangle for any expression a plus b to the power n. Using previous formula for a plus b to the power n, and we already know how to use Hayam Pascal triangle to write shortcut formula for this expression. Let's write a formula for a minus b to the power 5. And since a minus b can be written as a plus minus b to the power 5, we can use a previous formula for a plus b to the power n. First, let's write coefficients of our Hayam Pascal triangle and write 5, choose 0, plus 5, choose 1. Let's write it. Plus 5, choose 1, plus 5, choose 2, plus 5, choose 3, plus 5, choose 4, and plus 5, choose 5. We can calculate these coefficients easily using previous definition. Next, we write for our element a along the same line as we explained earlier. It will be a to the power 5 plus a to the power 4. Here we have a to the power 3, a to the power 2, a to the power 1, which is just a, and a to the power 0, which is 1. And for b, for minus b, we write this in opposite way. Minus b to the power 5, minus b to the power 4, minus b to the power 3, and minus b to the power 2, minus b to the power 1, and minus b to the power 0. And if we calculate these expressions, we can see that 5 choose 0 will be 1. We can calculate this easily because 5 choose 0 is equal to 5 factorial over 0 factorial, which is equal to 1 by definition, actually. And 5 minus 0 is again 5 factorial. 5 factorial over 5 factorial will be 1. And we can use it. So we have 1, a to the power 5, and minus b to the power 0 is 1. Here we have, if we calculate 5 choose 1, it will be 5. So we have 5 a to the power 4 minus b. And that's why we write here minus 5 a to the power 4b. Here we will have 5 choose 2 will be 10. It will be 10 a to the power 3 and b to the power 2. 5 choose 3 will be equal to 5 choose 2. This is also 10 a squared and b cubed. And since we will have here minus, we write here minus 10 a squared and b cubed. Here we have 5 choose 4 is equal to 5 choose 1 by previous feature of this object. It will be 5. So we have 5 a and b to the power 4. And last, 5 choose 5 will be equal to 5 choose 0. This is equal to 1. We do not write 1. This is a to the power 0 is equal to 1. So this is minus b to the power 5. And if we rewrite what we have, it will be a to the power 5 minus 5 a to the power 4b plus 10 times a to the power 3 b squared minus 10 times a squared b cubed plus 5 a b to the power 4 minus b to the power 5. So now we can write a shortcut formula for any mathematical expression a plus b to the power n, or a minus b to the power n, because we can write it as a plus minus b to the power n using Hayam Pascal triangle. It was everything for this tutorial. Like us and subscribe, and thank you very much for your attention. In this video tutorial, we will learn division of polynomials. At the end of this tutorial, you will be able to divide any polynomial p by another polynomial q with less degree, with degree which is less or equal, and we will have a remainder r. Also, we will learn the process of the long division, of how to divide one polynomial by another polynomial, and we will give a lot of examples. Like us and subscribe, and let's get started. First of all, let's begin with example. we have to gain understanding of division. Let's divide a polynomial 4a squared b plus 13ab squared and divide it by ab. In this case, it's very important to understand that this is equal to 4a squared b divided by ab plus 13ab squared divided by ab, which is 4a plus 13b, because we have cancellations here. I wanted to explain that in this case, in our example, when we divide sum of monomials, this is the sum of two monomial, and the result will be a polynomial. And if we divide the sum of two monomials by a monomial, in this case, quotient of a sum is equal to the sum of quotients. It's very important to realize. And if we divide a polynomial by a polynomial, the quotient, generally speaking, is not always a polynomial. For example, assume we divide a polynomial a squared plus x squared and divide it by a plus x. So we divide a polynomial by a polynomial. And in this case, this quotient cannot be represented as a polynomial. But another quotient, a squared minus x squared divided by a plus x, can be represented as a polynomial, because using algebraic identity shortcut multiplication formulas we learned earlier in this playlist, we can write a squared minus x squared as a minus x times a plus x. And in this case, we have a cancellations here, and the result will be a minus x. That's why our quotient can be represented as a polynomial. But in the first case here, this quotient cannot be represented as a polynomial. If you watched our arithmetic playlist in our channel, you can remember that any number can be divided by another smaller number and we will have a remainder. For example, if we have a number p and we want to divide this number p by number q, as a result, we have that p can be represented as q times some number m plus a remainder r. And in this case, remainder r is less than q, the divisor. As an example, assume we have p is equal to 33 and q is equal to 4. And we want to divide 33 by number 4. And in this case, 33 can be represented as 4 times 8, which is 32, and plus 1, which gives us 33. And 1, of course, is less than divisor 4. The same logic works for polynomials. And to define this division, first we have to define the concept of degree of a polynomial. Let's give a definition. Degree of a polynomial is the highest power of its letter. For example, assume we have a polynomial ax squared plus bx plus c. And we can denote this polynomial as some polynomial p, which depends on variable x. And of course, by definition, let's again repeat our definition. Degree of a polynomial is the highest power of its letter. And here, 2 is the highest power of its letter x. That's why, by definition, this polynomial, degree of this polynomial, p of x, is equal to 2. Assume another example. Assume we have a x to the power 4 plus b x to the power 3 plus c. Assume this is another polynomial, p1 of x. In this case, degree of the polynomial p1 of x will be, of course, 4, because the highest degree of its variable is 4. Along the same way, if we have a polynomial 123 x to the power 7 plus 1, in this case, this polynomial p2x, in this case, degree of our polynomial p2 of x is equal to 7, because this is the highest power of its variable, of its letter. It was the definition of a degree of a polynomial. Next, we can divide a polynomial. Assume we have a polynomial p of x, and we can divide our polynomial by another polynomial q of x. And of course, degree of q must be less or equal than a degree of p. In this case, when we divide, we will have as a result our polynomial p of x is equal to our divisor polynomial q of x multiplied by some another polynomial m of x plus a remainder r of x. And as for numbers, degree of our remainder r of x of this polynomial must be less than degree of a divisor polynomial q of x. Q of x. Let's give an examples, but before we have to understand that our remainder polynomial r can be a constant. In this case, the degree of our polynomial r is 0. For example, we can have that our polynomial r of x can be some constant c. It can be, for example, r can be 17, and in this case, 17, of course, is equal to 17 times x to the power 0. And in this case, this is equal to 1. That's why degree of our polynomial, remainder polynomial r, is 0. And the process of finding a quotient and a remainder is similar to the process of finding quotient and remainder for numbers. Watch our arithmetic course. Next, let's give and describe a division process for polynomials. Let's give a first example of polynomial division. Example number 1. Let's divide polynomial 8a cubed plus 16a to the power 2 minus 2a plus 4. This polynomial will be divided, and this polynomial is called the dividend. Dividend polynomial. And let's divide our polynomial by another polynomial 4a to the power 2 minus 2a plus 1. And this polynomial is a divisor. And this polynomial will divide our dividend. And result will be written here. And it will be a quotient. Quotient polynomial. Let's perform a division. First of all, we have to multiply our first member of our divisor by a monomial that will cancel off this first member of our dividend. And we will get rid of this first element. It will be clear from the example. Let's divide 4a squared by 2a. And of course, if we divide 2a by 4a, if we multiply 2a by 4a squared, we will have 8a to the power 3. Let's write it. 8a to the power 3. Next, we multiply 2a by the next element. 2a times minus 2a will give us minus 4a squared. Minus 4a squared. And one thing we have to understand that we have to write element of our polynomials correspondingly. So elements with the power 3 are written under elements with power 3, and elements with power 2 are written under elements with power 2. Next, we multiply 2a by last element of our divisor, and 2a times 1 will be 2a plus 2a. Next, we subtract. We perform a subtraction, and of course here we will have a cancellation. 8a cubed minus 8a cubed will be 0. Next, 16a to the power 2 minus 4a squared will be 20. Will be 20a squared. And minus 2a minus 2a will give us minus 4a. Minus 4a. And plus 4, this plus 4 is written next step will be we have to multiply 2a, this 2a, by we have to multiply this 4a squared by a monomial to get rid of this 20a squared. And of course, we have to multiply it by plus 5. Because if we multiply 5 by 4a squared, it will be 20a squared. So we will have 20a squared. And next 5 times minus 2a will be minus 10a. Minus 10a. And 5 times 1 will be 5. Next we perform a subtraction again. And 20a squared and 20a squared will be, we have a cancellation. And minus 4a minus 10a will give us plus 6a, or just 6a. And 4 minus 5 will give us minus 1. And at last we see that degree of our polynomial, which left, is 1. And degree of our remainder is less than degree of our divisor. That's why the process is finished. And this 6a minus 1 is a remainder. And that's why we can write that our dividend, let's write it here, our dividend 8, a to the power 3, plus 16, a to the power 2, minus 2a plus 4 can be represented as a quotient 2a plus 5 times a divisor 4a squared minus 2a plus 1 and plus a remainder 6a minus 1. Let's give another example. Example number 2. Let's divide a polynomial 6x to the power 4 plus 5x cubed minus 12x squared minus 8x plus 3. And let's divide our polynomial by divisor 3x minus 2. First of all, we have to get rid of this first element. That's why we multiply our divisor by 2x to the power 3. And since this times the first element gives us 6x to the power 4, we will get rid of the first element. Let's multiply next 2x to power 3 by minus 2. It will give us minus 4x cubed minus 4x cubed. Next, we perform a subtraction, and we will get rid of the first element of our polynomials. And when we perform a subtraction, we will have here 5 x to the power 3 minus 4x to the power 3 will give us plus 9 x to the power 3. And remainder of our polynomial will be, we have to just write it again. It will be minus 12 x squared minus 8x plus 3. Next, we have to get rid of this first element. That's why we multiply our remainder by plus 3x squared. Since when we multiply 3x squared by this divisor, we will have 3x squared times 3x will give us 9x cubed. 9x cubed. Next, 3x to the power 2 times minus 2 will give us minus 6x squared. Minus 6x squared, and that's all. Next, we perform a subtraction, and we have a cancellation of the first element. Next, minus 12 x to the power 2 minus 6 to the minus 6x squared will give us minus 6x squared. And let's rewrite what we have left here. Next, we have to multiply our divisor by minus 2x because we want to get rid of this element. That's why if we multiply minus 2x by a divisor, we will have minus 6x squared and plus 4. If we perform a subtraction, we have a cancellation of the first element, and remainder will be minus 12x plus 3. Next, we multiply to get rid of this element. We have to multiply by minus 4. And if we next multiply minus 4 by a divisor, we will have minus 12x plus 8. And if we perform a subtraction, we have a cancellation of the first element, and plus 3 minus 8 will give us minus 5. And this minus 5 is a remainder polynomial with, since degree of polynomial minus 5 is 0, and 0 is less than 1, and 1 is a degree of divisor polynomial. That's why if we write a result of our process, let's write it here, we will have that 6x to the power 4 plus 5x to the power 3 minus 12x squared minus 8x plus 3 is equal to divisor 3x minus 2 multiplied by what we left here, 2x cubed plus 3x squared minus 2x minus 4 and plus a remainder which is minus 5. It was quite a complex example, and let's assume another last example. Last example number 3. Let's divide polynomial 2x to the power 5 plus 3x to the power 3 minus x squared plus 4x plus 1. And let's divide this polynomial by a polynomial x squared minus x plus 2. It's very important to note that here we actually have a 0 times x to the power 4. But since we do not have this element, but here in this process we have to write it because we want to write one polynomial and another polynomial correspondingly, degree by degree. And so we want to divide this polynomial by this polynomial, and result will be written here. First, we want to get rid of this element of our polynomial, and that's why we have to multiply our divisor by 2x to the power 3. And if we multiply 2x to the power 3 by this polynomial, we will have we will have 2x to the power 5 minus 2x to the power 4 plus 4x to the power 3. And if we subtract, we will get rid of this first element, and a result will be 2x to the power 4 minus x to the power 3 minus x squared plus 4x plus 1. Next, we want to get rid of this element. That's why we multiply our divisor by a monomial plus 2x squared. And if we multiply 2x squared by our divisor, we will have 2x to the power 4 minus 2x to the power 3 plus 4x squared. Next, we perform a subtraction, and we will get rid of this first element. And the result will be x cubed minus 5x to the power 2 plus 4x plus 1. Next, we want to get rid of this first element, and we have to multiply our divisor by plus x. Next, if we multiply plus x by a divisor, we will have x to the power 3 minus x squared plus 2x. And we perform a subtraction as usual, and we will get rid of this first element, and result will be 4 minus 4x squared plus 2x plus 1. Next, we want to get rid of this element, and we multiply our divisor by minus 4. And since minus 4 times this polynomial will give us minus 4x squared plus 4x minus 8, and we have to perform a subtraction, and as a result it will be minus 2x plus 9, and we have a cancellation here, and the process is over. And since the degree of this remainder is 1, degree is equal to 1, which is less than degree of a divisor, which is 2. And let's rewrite result of our process. So 2x to the power 5 plus 3x to the power 3 minus x squared plus 4x plus 1 is equal to divisor x squared minus x plus 2 times 2x to the power 3 plus 2x squared plus x minus 4 and plus a remainder which is minus 2x plus 9. And that's a result. So our polynomial is represented as this polynomial times this polynomial and plus a remainder. It was everything for this tutorial. Thank you very much. Like us and subscribe. In previous tutorial, we learned how to divide one polynomial by another polynomial. And now we will learn remainder theorem of Bezou. This is very useful result and will help you to find roots of equations. Let's get started. Don't forget, like us and subscribe. To formulate Bezou theorem, let us assume we have a polynomial p of x, and let us divide this polynomial by this polynomial. It's also called a binomial. And if we divide this our polynomial by this binomial, we will have watch our previous tutorial on how to divide one polynomial by another polynomial. We will have x minus a times some another polynomial q of x plus a remainder. And as we already know, degree of this polynomial r of x must be less than degree of a divisor x minus a. But degree of divisor, degree of our divisor x minus a is 1. So this is 1. That's why degree of remainder r, which is less than 1, must be 0. And our remainder must have the form of some constant times x to the power 0, which is 1. Or this is just some constant r. And since, let's do it here, using this representation, call it representation 1, we have, it follows from representation 1, instead of this r, if we put the constant r, we will have p of x is equal to x minus a times q of x plus some constant r. This is a constant, some number. And that's why if we put, instead of this x, we put a, we will have p of a is equal to a minus a times q of x plus r. Because this a minus a is 0, this part will be equal to 0. And we will have that p of a is equal to r, which means that our remainder r is equal to p of a. This is the result of French mathematician Bezou. And let's formulate our theorem. Bezou. It was this result of this year's. I'm writing here. Bezou Theorem. A remainder after division of polynomial p of x by binomial x minus a is equal to p of a, or the value of our polynomial at the point a, where a is a constant. Let's repeat it. Remainder after division of polynomial by a binomial is equal to this constant, which can be calculated as a value of our polynomial at a. Let's assume an example. Let's give an example. Assume we have a polynomial p of x is equal to x to the power 3 minus 3x squared plus 5x minus 1. Assume we divide our polynomial by this binomial, and we have to find a remainder. Find remainder. Easily using previous theorem by Bezou Theorem, we have that remainder r is equal to our polynomial p at the point 2. And this is equal to 2 to the power 3 minus 3 times 2 squared plus 5 times 2 minus 1. If we calculate it, it will be equal to 5. So using Bezou theorem, we can easily find remainder after division of our polynomial by this binomial. Let's check it using previous technique on how to divide one polynomial, x to the power 3 minus 3x squared plus 5x minus 1. And let's divide it by a binomial x minus 2. I will do it quite quickly. If you don't understand it, watch our previous tutorial. We perform a subtraction and we have a cancellation here. It will be minus x to the power 2 plus 5x minus 1. Now here we have minus x, and if we multiply this minus x by this divisor, we will have minus x squared plus 2x. After a subtraction, we will have 3x minus 1. And here we have to write plus 3. We will have 3x minus, not minus 1, but minus 6. And after subtraction, we have cancellations here. And minus 1 minus minus 6 will be 5. So after manual calculation, we also have a remainder 5. That's why using Bezou theorem, we can easily find remainder after division of polynomial by a binomial. Once again, it's very important to understand that when we divide our polynomial by this binomial, degree of remainder must be less than degree of this divisor, x minus 2. And degree of divisor x minus 2 is equal to 1. That's why degree of a remainder must be less than 1, which is 0. It must be a constant. So this is always a constant. We found this constant. It was 5, and we checked it using simple long division, and we proved that this is really number 5. Let's continue and give a very important corollary of Bezou theorem. First of all, we have to define what is the root of our polynomial. Let's give a definition. Let's give a definition. Number A is a root of polynomial p of x, or we can equivalently say that this is a root of equation p of x is equal to 0. This is the same thing. The root of this polynomial means, by definition, this is if and only if when p of a is equal to 0. So when we insert number a in our polynomial and it will be equal to 0, then number a is a root of our polynomial, or this is the root of this equation. Graphically, this looks like this. Assume we have the chart of our polynomial. This is the graphic of our polynomial, and this intersection, assume this is the number a. Assume this is number a, and that's why here number a is root of our polynomial, because when we insert number a in our polynomial, we have 0. Very important corollary of our Bezou theorem is that a is root of polynomial p of x if and only if when p of x can be divided by a binomial x minus a with a 0 remainder, or our number r is equal to 0. So these two facts are equivalent. When a is the root of our polynomial, then our polynomial can be divided by x minus a, and remainder will be 0. Let's prove our theorem. This can be done very easily. When we divide our polynomial p of x by a binomial x minus a, we have a representation p of x is equal to x minus a times some polynomial q of x plus a remainder r. And when we insert instead of x number a, then we have this. And since a minus a is equal to 0, this member will be 0. And that's why p of a is equal to r. And when our r is equal to 0, then we have p of a is equal to 0, or equivalently, a is the root of our polynomial. That's why if we want to prove to this side, when a is the root of our polynomial p of x, or this, we must have r equal to 0. Remainder must be 0. And opposite, when remainder is equal to 0, then we have p at the point a is equal to 0, or a is the root of our polynomial. So this was the proof of our result. Our next example, assume we have a polynomial p of x is equal to x to the power 3 plus 5x squared minus 18. This polynomial can be divided by a binomial x plus 3. And this x plus 3 can be written as x minus 3. And let's divide our polynomial by this binomial. And we know from Bezou theorem that in this case a remainder will be equal to p at the point -3. And if we calculate, we will have -3 to the power 3 plus 5 times -3 squared minus 18, which is equal to minus 27 plus 5 times 9 minus 18. This is equal to 0. And since remainder is equal to 0, it means that number -3 is the root. This is a root of polynomial p of x. Another very important result that follows from Bezou Theorem is that assume we have a polynomial p of x, and it has a, let's give an example. Assume we have a polynomial x to the power 2, x squared minus 4x plus 3. And first of all, this result is formulated like coefficients. Here we have 1. Coefficients of our polynomial must be integer, and any integer root of our polynomial must divide our free member coefficient with that corresponds to x to the power 0. This is 1. And we always avoid writing this, but we look at the free coefficient. This is called free member or free coefficient of our polynomial. And any integer root of our polynomial must divide our, in this case, number 3. That's why if we have integer root of our polynomial, these roots can be plus or minus 1, because plus and minus 1 divide our number plus 3. And it can be plus or minus 3. And we can search the root of our polynomial, of our equation x squared minus 4x plus 3 equal to 0. Among these numbers, these 4 numbers, plus minus 1 and plus minus 3. Of course, we assume that roots of our equation are integer. Why is that? Because when we have, for example, 2 roots of our polynomial, of our equation, p of x must be equal to x minus a times x minus b. And in this case, and a and b are roots of our equation, because when we insert instead of x number a, we will have 0, because this factor will be 0. And again, if we insert instead of x number b, we also will have a 0, because this factor will be 0. So a and b are roots of our equation. And since we can write our polynomial as, let's perform multiplication, it will be x squared minus bx minus ax plus ab. Or this can be written as x squared minus x, or plus ab. And this this free member of our polynomial is equal to AB. Assume this is n. So our n is equal to AB, and roots of our polynomial a and b must divide our number n. That's why, let's repeat it again, integer roots of our polynomial must divide our free member. Let's give one more example in this case. Let's prove that let's search the roots of our polynomial among these numbers. Let's give an example for this result. Example, for polynomial p of x equal to x squared minus 4x plus 3. Let's search the roots of our polynomial from result that follows from Bezou Theorem. We know that we have to search roots, integer roots of our equation among numbers plus minus 1 and plus minus 3. And if we insert instead of our variable x number 1, we will have 1 squared minus 4 times 1 plus 3. It will be 0. That's why number 1 is the root of our equation. And we can divide now our polynomial x minus x squared minus 4x plus 3. We can divide this by x minus 1, because 1 is the root of our polynomial. And when we perform a division, let's perform our division very quickly. We have a cancellation here. And we will have here minus 3x plus 3 minus 3 minus 3x plus 3. And when we perform a subtraction, we will have a 0. So when we divided our polynomial by this binomial divisor, we had a quotient. In other words, our polynomial p of x is equal to x minus 1 times x minus 3 plus a remainder which is equal to 0. And that's why we can found the second root of our equation. And since from the result previously given, we have that since x minus 3 divides our polynomial, that's why number 3 is the second root of our polynomial, of our equation. It was everything for today. Like us and subscribe, and good luck. In this video tutorial, we will learn some very special formulas in algebra. In algebra, these formulas are used very often, and you have to know and use these formulas because these formulas are very important. Let's get started. Like us and subscribe. So this special formula in algebra looks like when we have such a polynomial, x to the power m minus a to the power m, this polynomial is divisible by x minus a, and the result of the division is some another polynomial of degree m minus 1. Because, first of all, we had a polynomial of degree m, and we divide our polynomial by another polynomial of the degree 1, and resulting polynomial will be a polynomial of degree m minus 1. In particular, the special case of this formula for m equal to 3 is very famous formula when x to the power 3, x cubed minus a cubed, is represented as x minus a times some another polynomial of degree 2. How to prove these formulas? First of all, we have to know Bezou theorem we gave in our previous tutorial. That's why to understand our tutorial, you have to watch our previous tutorials. That's why very important to watch our algebra playlist consequently, tutorial after tutorial, and you will have a very strong understanding of beginning of algebra. Let's begin to prove our formula. First of all, from previous tutorials, we know that assume a polynomial p of x which is equal to x to the power n minus a to the power n. Special case when n is equal to 2. First of all, let's assume that x is equal to 1. That's why x minus a can be represented as x minus a to the power multiplied by 1. Because x minus a is divisible by x minus a. When our n is equal to 2, we have x squared minus a squared. And from shortcut special formulas we gave earlier, we know that this can be represented as x minus a times x plus a. And that's why, because of this representation, this polynomial x squared minus a squared is divisible by x minus a. And the quotient or result of this division is equal to x plus a. That's why this representation is valid. We already know this from previous tutorials. But what if we have a higher degree, for example, x to the power 3 minus a to the power 3? In this case, we will show that our polynomial p, let's denote this as pn of x, and let's call it p3 of x, which is equal to x to the power 3 minus a to the power 3. Let's show that this polynomial is divisible by x minus a. And to prove this, that our polynomial is divisible by x minus a, we can use two methods. The first method is manual division. How to divide one polynomial by another polynomial? Watch again our previous tutorials. The second is to use Bezou formula, or Bezou, not formula, but Bezou theorem. Again, watch our previous tutorials. We will prove this using both methods. Let's prove first, by first method, by manual division. Let's divide x to the power 3, x cubed minus a cubed, and divide it by x minus a. And we will show that remainder of this division is equal to 0. That's why x cubed minus a cubed is divisible by x minus a. Let's perform a division. How to perform a division? Again, watch our previous tutorial in Algebra playlist. We write here x squared. X squared times x minus a is, first of all, let's write our polynomial as x cubed plus 0x squared plus 0x and minus a to the power 3. And x squared times x minus a is equal to x to the power 3 minus ax squared. And if we perform a subtraction, we have a cancellation here, and result will be 0 minus ax squared is equal to ax squared, and we have to rewrite the rest. Next, we write here plus ax, and when we divide ax by x minus a, we have ax squared minus a squared x. And if we perform a subtraction, we have a cancellation here, and result of the subtraction will be a squared x minus a cubed. And next we write here plus a squared, and when we multiply x squared by x minus a, we have a squared x minus a cubed. And after subtraction, we have cancellation, we have total cancellation, and result will be 0. That's why we are showing here, let's write it here, that this polynomial x cubed minus a cubed, x cubed, x to the power 3 minus a to the power 3, is divisible by x minus a, and that's why it can be represented as x minus a times another polynomial, this polynomial result of division, a quotient, and this polynomial is equal to x squared plus ax plus a squared. So we have a result. This formula is very important in algebra, and by using, it was the first way, and using the second way, we also can prove that x cubed, using theorem of Bezou, x cubed minus a cubed is divisible by x minus a. How theorem of Bezou is used? We just take our p3 of x, this polynomial, and insert instead of x number a, and since it will be equal to 0, that's why a remainder is a 0, and that's why our polynomial is divisible by x minus a. And what will be the result of this division? We already showing here. The result will be this polynomial, and that's why we have a result, because we had a result for n1, for n equal to 2, and for n which is equal to 3, we have a result that it will be x minus a times x squared plus ax plus a squared. We can continue our process for any n, and the final result for any n, for any positive integer n, will be x to the power n minus a to the power n is divisible by x minus a. And the quotient, or the result of this division by x minus a, is equal to, it must be the polynomial of degree x of degree n minus 1. So it will be x n minus 1 plus a x n minus 2 plus result, or sorry, degree of a will decrease, it will be a squared, and degree of x will decrease, it will be n minus 3 plus so on. And here we will have n minus 1, and here we will have x n minus n, which is 0, and this will be equal to 1. So this is our important formula in algebra, and we have to remember it. How to prove this formula? We can use the same method for n3. Why this polynomial is divisible by this polynomial? Again, we have to use Bezou formula, Bezou theorem, because our polynomial xn minus an, because Pn of a, if we insert instead of x our a, is equal to a to the power n minus a to the power n, which is 0. Because this is 0, remainder of division will be 0. That's why our polynomial xn minus an is divisible by x minus a, and result of this division can be found for any n using manual division. That's all. That's why Bezou theorem is very important in algebra. Watch previous tutorials. This formula is very important in algebra. In particular, using this formula, we can calculate the sum of geometric progression. I will show how to use this formula for the sum of geometric progression in next tutorial. So watch our next tutorial. It was everything for this tutorial. Thank you very much. If you liked my video, like and subscribe us. Have a great day. In this video tutorial, we will learn sum of geometric progression. After this tutorial, you will be able to find the sum of geometric progression with finite and infinite number of elements. Like us and subscribe, and let's get started. First of all, let's define what is a geometric progression. This is a sequence. Assume, let's fix some number a, and let's write powers of this number: a to the power 0, a to the power 1, a to the power 2, a to the power 3, and so on, a to the power n. And let's assume the sum of these elements. And let's denote it as Sn. And how to find Sn, the sum of elements of our sequence, and this sequence is called geometric progression. Let's prove it. To prove this result, first of all, we have to remember our previous special formula in algebra that looks like x to the power n minus a to the power n. This polynomial, as we know from previous tutorial, is divisible by another polynomial or binomial x minus a. And the result of this division is equal to some polynomial of degree n minus 1. Exactly, if you write it, this is x to the power n minus 1 plus a times x to the power n minus 2 plus a squared. So degree of a will be increasing times x to the power n minus 3, and degrees of x is decreasing, plus and so on. And last member is a to the power n minus 1 times x to the power n minus n, which is equal to x to the power 0, which is 1. And look at this formula. This formula is valid, and we proved it in our previous tutorial. And if we put x such that equal to 1, then we have to the right side of our previous equation, write it as equation 1. Then from equation 1 we have, to the right side of this equation we have, since x is equal to 1, we have 1 plus a squared plus so on, a to the power n minus 1. And to the left side of our equation we have 1 minus a to the power n divided by 1 minus a. And that's all. This is the formula for the sum of the first elements of geometric progression. In other words, the other representation, how we write this formula, is Sn is equal to 1 minus a to the power n, Sn minus 1 is equal to a minus a to the power n divided by 1 minus a. Or we can write it as Sn is equal to 1 minus a to the power n plus 1 divided by 1 minus a. This is the formula for the sum of the first n elements of geometric progression. Of course, our geometric progression can have infinite number of elements. Assume we have a1 plus a squared plus a cubed plus and so on, a to the power n plus up until infinity. And assume absolute value of a is less than 1. In this case, since our sum is equal to 1 minus a to the power n plus 1 divided by 1 minus a, and this element, since we have infinite number of elements, will tend to 0. And don't worry if you don't understand it. We will learn limits in our next tutorials when we will learn calculus. But anyway, you have to understand that this member of our equation, which is less than 1, if we take the powers of this number and the power is increasing, in this case, our number is decreasing and tends to 0. So Since this is 0, resulting formula will be 1 divided by 1 minus a. And this is the formula for the sum of infinite number of elements of geometric progression. That's all, very easy. Sometimes we can have that in our geometric progression, the first element is not 1, but some number b. Let's put here b. In this case, in our formula, we have here b, and everything else remain the same. Let's give several examples. Example number 1, assume we have a equal to 5. And let's assume the sum of elements of our geometric progression 1 plus 5 plus 5 squared plus and so on 5 to the power 10. And using our previous tutorial, using our previous definition of geometric progression, it will be this formula for n elements of our geometric progression. So we have 1 minus a to the power n plus 1 divided by 1 minus a. And we write it like this, but here we have a is equal to 5 and n equal to 10. It will be 1 minus 5 to the power 11 divided by 1 minus 5. It will be negative number 1 minus 5 to the power 11 divided by negative number minus 4. And we can write it as 5 to the power 11 minus 1 divided by 4. And this is the answer of our example. Next example, assume we have sum of our next sequence 1 plus 1 over 2 plus 1 over 4, and of course 1 over 4 is equal to 1 over 2 squared plus 1 over 8, and this is 1 over 2 to the power 3 plus and so on plus 1 over 2 to the power n. The sum of this geometric progression is equal to 1 minus a to the power n plus 1 divided by 1 minus a. And we have a is equal to 1 over 2, and n is, as usual, n will remain n, and it will be 1 minus 1 over 2 to the power n plus 1 divided by 1 minus 1 over 2. 1 minus 1 over 2 is 1 over 2, and if we divide by 1 over 2, it will be multiplication by 2. So answer will be 2 times 1 minus 1 over 2 to the power n plus 1. Of course, in this example, we can have infinite number of elements here. Assume here n is tending to infinity. In this case, our example will be 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 and plus and so on 1 over 2 to the power n plus and so on infinite number of elements. The sum of this progression will be this answer, our previous answer, but we have to tend n to infinity. In this case, this member will tend to 0 because we have a number with absolute value less than 1, and if we increase the power, because 1 over 2 to the power n, if we tend n to infinity, will tend to 0. If you don't understand this, don't worry. We will learn limits in our next tutorials on calculus, but for the moment, assume that this member will tend to 0. In this case, answer will be 2. So sum of this geometric progression is equal to 2. Now we can find the sum of geometric progression with finite or infinite number of elements. It was everything for this tutorial. Like us and subscribe, and have a good day. In this video tutorial, we will learn next special formulas in algebra. Divisibility of this binomial, this polynomial, by x plus a. In particular, we will learn that in general case, xn minus an can be divisible by polynomial or binomial x plus a, and resulting quotient after division will be this. So we have a very nice formula. This formula is very useful in algebra. So watch us further. At the end of this tutorial, you will be able to prove this formula and use it. Like us and subscribe, and let's get started. So first of all, from previous tutorial, we know that for polynomial p of x, x to the power m minus a to the power n, this polynomial is divisible by x minus a, because using Bezou Theorem, p of a is equal to a to the power m minus a to the power m, which is 0. And remainder after division of this polynomial by this polynomial will be 0. And that's why this polynomial divide our polynomial exactly. So we had nice formula when x to the power m minus a to the power m is equal to x minus a times something, and here we had a polynomial of degree m minus 1. The same works when instead x minus a, we assume x plus a. So we have a natural question. Natural question is polynomial p of x which is x to the power m minus a to the power m is divisible by x plus a, not minus, but x plus a. Answer is yes. But for even number n, even number m. In this case, in mathematics, we write that m is equal to 2 times some integer number k. So if our number m is even and can be represented as 2 times some integer number k, in this case, our polynomial is divisible by x plus a. Why? Because again, using Bezou theorem, p of x when x is equal to minus a, because here x plus a can be represented as x minus a. And we already know how to use Bezou theorem. If you don't know this theorem, watch our previous tutorials. If you don't understand anything in our tutorial, watch our previous tutorials, all the playlists, because our playlist is done in this way that if you want to understand one tutorial, you have to know our previous tutorials. And if you watch our playlist from the beginning until the end, you will have a very deep understanding of algebra. In this case, when we put instead of x number minus a, we will have minus a to the power m minus a to the power m. In this case here, look at this minus a to the power m. This is equal to, it has two cases when m is even and can be represented as 2k. We know that even numbers are divisible by 2. These numbers are 2, 4, 6, 8, and so on. So m has a representation 2k. In this case, minus a to the power m is equal to a to the power m. And when m is not represented as 2 times k, this is minus a to the power m. That's why this is equal when m is even. That's why when our m is even, in this case, divisibility is valid and remainder will be 0. And we have a special formulas in this case. Assume our n is 2 or our m is 2, it doesn't matter. Assume, let's use letter n. In this case, x squared minus a squared, as we know previously, we have a representation x minus a times x plus a, and this is divisible by x plus a. When n is equal to 4, in this case, x squared minus a squared can be represented again using shortcut multiplication formula. Watch our previous tutorials. Is equal to, here we have x to the power 4 minus a to the power 4. This is x squared minus a squared times x squared plus a squared. And since, in this case, the first brackets can be represented as x minus a times x plus a, in this case, our polynomial is divisible by x plus a. So our polynomial is divisible by x plus a. And let's write it further. This is equal to x plus a times x minus a times x squared plus a squared. And if we multiply these two brackets, this will be some polynomial, write it q of x, and degree of this polynomial must be 3, because we're multiplying two polynomials, one polynomial with degree 1 times the second polynomial with degree 2. And of course, here we're dividing the polynomial of degree 4, dividing by the polynomial of degree 1. And the resulting polynomial will be the polynomial with degree 3. We can use manual division for polynomials, but the general rule is that x to the power 4 minus a to the power 4 is divisible by x plus a. That's why we have a representation x plus a times, and quotient or result of the division will be polynomial of with degree 3. It will be x 3, x to the power 3. Next member will be a x2. So degree of a is increasing and degree of x is decreasing. Next member will be a squared x, and next member will be a to the power 3 and x to the power 0, which is 1. Next, we have to write, first we write minus, then plus, then minus. Next, let's write for n, which is 6, and we have x to the power 6 minus a to the power 6 is divisible by x plus a. That's why it can be represented as x plus a times some polynomial of degree 5. And this polynomial is written as x to the power 5. Next member will be a and x to the power 4. Next, we decrease the power of a. It will be a squared, and increase and decrease the power of x. It will be x to the power 3. Next, we increase a, power of a. It will be a to the power 3, and decrease the power of x. It will be a squared. Next element is a to the power 4, x, and next will be a to the power 5, and we don't write x to the power 0, which is 1. And we write first minus, then plus, minus, then plus, and then minus. So this is our special algebraic formula, and how this formula can be read. This polynomial is divisible by this polynomial. That's why we have a representation. This representation, and result of this division or quotient is this. This quotient can be found using simple manual division, or it's also called long division of polynomials. But I'm showing here for you how to write this formula, how to remember this formula. Next, we have to notice that our polynomial x to the power n minus a to the power n for even n, or when n is equal to 2 times k, is divisible by x minus a, as we know from previous tutorials, and x plus a. So our polynomial is divisible by x minus a and x plus a. That's why our polynomial is divisible by x minus a times x plus a, which is x squared minus a squared. And if we again use manual multiplication and Bezou theorem, not Bezou theorem, but simple multiplication, because Bezou theorem works only for when we divide by monomial of degree 1. Here we have monomial of degree 2. That's why Bezou theorem is not used. We just have a notice here. That's why for n4, for example, we have x to the power 4 minus a to the power 4 can be represented as x squared minus a squared times x squared plus a squared. And that's why our polynomial is divisible by x squared minus a squared. Assume n is equal to 6. In this case, x to the power 6 minus a to the power 6 is divisible by x squared minus a squared. That's why it has a representation x squared minus a squared. Now we can use simple long division of polynomials, and quotient, or result of this division, can be found. It will be x to the power 4. Of course, here we will have a quotient with degree 4 because we are dividing the polynomial of degree 6 by polynomial of degree 2. And result will be some polynomial of degree 4. It will be x to the power 4 plus, we always have plus here. You can divide it manually. Plus, we increase the power of a by 2 times x, and we decrease the power of x by 2. Next, we again increase power of a by 2 and decrease power of x by 2. It will be x to the power 0, which is 1. So this is formula for n, which is 6. Let's at last write our formula for n, which is 8, and write x to the power 8 minus a to the power 8. This polynomial is divisible by x squared minus a squared, and result of this division is x to the power 6 plus a squared x to the power 4 plus a to the power 4 x squared plus a to the power 6. And general case is x to the power n minus a to the power n, and of course n is even. This is divisible by x squared minus a squared, and we have a representation Here we have x to the power n minus 2 plus a squared, x to the power n minus 4 plus a to the power 4 times x to the power n minus 6 plus etc. plus a to the power n minus 2, and here we have x to the power 0, which is 1. So this is general formula for our representation. It was everything for today. Thank you very much, and like us and subscribe. Have a great day. In this video tutorial, we will learn special formulas. This is part 3 of our tutorials on divisibility of binomial, of this binomial by this binomial. In this tutorial, we will learn is binomial x to the power n plus a to the power n divisible by x plus a. We will learn that in some cases we have a divisibility. We will use Bezou Theorem to prove it, and result or quotient of this division will be another polynomial with degree n minus 1. Like us and subscribe, and let's get started. Let's give a natural question. Is a polynomial p of x, which is x to the power n plus a to the power n, is this polynomial divisible by a binomial x plus a? Answer is yes, but n must be odd. Odd, I mean it must be 1, 3, 5, 7, and so on, not even numbers. How to prove it? Using Bezou theorem. Using Bezou theorem, since this binomial x plus a can be represented as x minus a. If you don't know how to use Bezou theorem, watch our previous tutorials, watch our playlist, and you will understand everything in this tutorial. Since x plus a is equal to x minus a, we calculate of our polynomial p of x when x is equal to minus a. It will be the polynomial at the point minus a, which is we have two cases, which is minus a to the power n plus a to the power n, and when here it will be equal to, when n is odd, it will be minus a to the power n, and when n is even, not odd, it will be a to the power n. So the result will be a 0 when n is odd, and when n is even, it will be 2an, which is not 0. That's why the only case when we have a 0 here, and by Bezou theorem, remainder of after division will be 0, so we have exact divisibility of our polynomial by this binomial when n is odd. All in all, when n is odd, our polynomial is divisible by this binomial because we have here 0, or the value of our polynomial at the point x equal to minus a is 0. This is using of Bezou theorem. Next, let's write our representation because we have exact division for different n. Assume n is 3. In this case, x to the power 3 plus a to the power 3 is equal to x plus a times some polynomial of degree 2. Since this polynomial is divisible by this polynomial, we have this representation. And the quotient, or this polynomial, can be found using manual long division. Watch how long division is done. Just divide this by this, and you will find this. But I will give you the rule how to write it. Here we will have, since this is the polynomial of degree 2, this will be x to the power 2. Next member will have a with a bigger degree and x with smaller degree. Next, it will be with bigger degree, a squared, and x with smaller degree, x0, which is 1. Next, we write minus and plus. This was formula for n3. Let's write formula for n, which is 5. So x to the power 5 minus a plus a to the power 5 will be equal to x plus a times our quotient polynomial will be degree of 4. So we write x to the power 4. Next will be a x to the power 3. Next it will be a squared x squared. Next it will be a cubed x, and next it will be a to the power 4. We write minus, plus, minus, and plus. So this is formula for n, which is 5. And let's write our formula for general n. For general n, it will be xn plus a to the power n is equal to x plus a, and quotient polynomial will be the polynomial of degree n minus 1. It will be x to the power n minus 1. Next member will be a x to the power n minus 2. Next it will be a squared times x to the power n minus 3. And last, and so on, and last member will be a to the power n minus 1. We write here minus, plus, minus, and so on, and plus. This is the general formula for representation of xn plus an. Since it's divisible by x plus a, we have a representation of x plus a times some another polynomial with degree n minus 1, which is found after division of this polynomial by this polynomial. These formulas are very important, and you have to watch these tutorials to use it when you solve algebraic equations and another algebraic problems. Thank you very much for your attention. Like us and subscribe. In this, our math video tutorial, we will repeat all shortcut multiplication formulas in algebra we already learned in our previous math video tutorials, since these formulas are very important in mathematics. First of all, let's begin with shortcut multiplication formula: x squared minus y squared, which is equal to x minus y times x plus y. To prove this formula, we have to multiply these two brackets. So we first multiply x by x and then x by y. And then we multiply y by x and y by y. We already did it in our previous tutorial, so watch our previous tutorials and you will understand every formula I will repeat in this tutorial. So we will have x squared plus xy minus xy plus, minus y squared. And we will have cancellation here. And after cancellation, it will be equal to x squared minus y squared. Next formula, very famous formula, and we will use this formula very often in our calculations. It's shortcut multiplication formula for x plus y squared. So this is equal to x squared plus 2xy plus y squared. This formula is also very easy to prove. X plus y squared is equal to x plus y times x plus y. So if we perform multiplication, it will be equal to x squared plus xy plus xy plus y squared. And these two xy will be equal to 2xy. So we proved our formula. Another variant of this formula is x minus y squared, not plus but minus. This is equal to x squared minus 2xy plus y squared. To prove this formula, again we have to multiply x minus y by x minus y. It will be x squared minus xy plus y squared. And these two minus xy's give us minus 2xy. So this formula, these two formulas combined can be written as, because since we have here plus and plus, here we have minus and minus, combining these two formulas we can write x plus minus y squared equal to x squared plus minus 2xy plus y squared. Next shortcut multiplication formulas is x plus minus y to the power not 2 but any power n. This is called binomial theorem, or this formula also called binomial of Newton. Binomial of Newton. And to write shortcut multiplication formula for this case, we use Hayam Pascal triangle. In previous tutorials, I already gave a definition what is Hayam Pascal triangle and how to construct this triangle and how to use this triangle to write binomial theorem or binomial of Newton. Let's do it again for case when n is equal to 3. In this case, first of all, we have to construct Hayam Pascal triangle. This is done in this way. So first of all, we write number 1 at the corner of this triangle or this pyramid. Next, we write it in this point, we write the sum of these two elements. It will be 2. At this point, we write the sum of these two elements, which is 3. Here, we also write 3, the sum of these two elements. Here, we write the sum of these two elements, and we will have 4. Here we will have 6, and here we will have 4. This triangle is used to write shortcut multiplication formula for example, x plus minus y to the power 3. And first of all, we write x to the power 3. I am giving you certain rule how to remember this formula. We write x to the power 3. Next, we write x with power less by 1, which is x squared, and write y. Here we had y to the power 0, but we do not write it because this is equal to 1. Next member is x with less power, just x, and y with power 2. And next, here we have y to the power 3, and here we had x to the power 0, but we do not write it. Next, we have here the certain levels of our triangle: level 0, level 1, level 2, level 3, and level 4. Here we use the level 3 because here we have power 3. And we use coefficients 1, 3, 3, and 1. So here we have 1. We do not write it. 3, 3, and 1. And to write the signs, here we have plus. Here we have minus, y minus, because, here we have plus minus. Because if here y is with the sign plus, here we had just y to the power 1, and it will leave sign plus. If we had the sign minus, here we had y with the power, with the sign minus, and it will remain. Whereas here, since we have y to the power 2, so in this case, plus y and minus y will be transformed into plus y squared. So here we will have always plus. And a last sign will be again plus and minus, because we have here y to the power 3. And again, let's write it separately. Plus minus y to the power 3 is plus minus y to the power 3. This is obvious because y to the power 3 is equal to y to the power 3, and minus y to the power 3 is equal to minus y to the power 3. So it was binomial theorem for the case when power is equal to 3. Let's write a binomial expansion. It's also called expansion for case when n is equal to 4. And this is done easily. And here we use the line number 4 in our Hayam Pascal triangle. So we have x plus minus y to the power 4 is equal to x to the power 4, x to the power 3y, x to the power 2, y to the power 2, x and y to the power 3, and y to the power 4. Next, we use these coefficients. And these coefficients are 1, 4, 6, 4, 1. So we have here 1, 4, 6, 4, 1. And we do not write number 1. Next, we have to write the signs plus or plus minus. Since here we have y with power 1, we write plus minus. And since here we have y with power 2, we will have always plus. Since here we have y to the power 3, we have plus minus. And here, since we have y to the power 4, we have always plus. So it was shortcut multiplication formula or binomial expansion when n is equal to 4. To write next shortcut multiplication formulas, we have to repeat the divisibility of x to the power n plus y to the power n. We have two cases here. Divisibility by x plus y and x minus y. We also had another binomial, x to the power n minus y to the power n. And we had two cases, x plus y and x minus y. In previous tutorials, we already learned that here, for first case, we have divisibility, but n must be odd. Odd numbers are 1, 3, 5, not divisible by number 2. Here, we didn't have a divisibility, and we can prove it using Bezou Theorem. Next, case number 3, we have here also divisibility. So x to the power n minus y to the power n is divisible by x plus y. But for number n, which is even number is 2, 4, 6, number must be divisible by 2. And here, last case, we always have divisibility. That's why for first case, we have a representation because of divisibility. X to the power n plus y to the power n is equal to x plus y times some polynomial. And n here must be odd, or it can be represented as some number 2 times some integer number plus 1. Here we have nothing. We have nothing. So in other words, x to the power n plus y to the power n cannot be represented as x minus y times some polynomial. In this case, when n is even, we also have a representation x to the power n minus y to the power n. For n which is even, or can be represented as 2 times some integer number k, is equal to x plus y times some polynomial. And of course here, the degree of this polynomial must be n minus 1. We know it from previous tutorials. And last case, x to the power n minus y to the power n is always, for even and odd n, is equal to x minus y times some polynomial of degree n minus 1. Let's repeat how to prove this case number 2, why this polynomial x to the power n plus y to the power n is not divisible by x minus y. To prove this, we have to repeat Bezou theorem. Bezou theorem was explained in our previous tutorials. It states that the polynomial p of x is divisible by a binomial x minus y when p at y is equal to 0. In our case, we had a polynomial x to the power n plus y to the power n. So our polynomial p of x is equal to x to the power n plus y to the power n. And our polynomial at point y is equal to y to the power n plus y to the power n, which is not equal to 0, and that's why we do not have divisibility. And that's all. Next, let's repeat these representations for cases 1, 3, and 4. Let's do it. The first case, x to the power n plus y to the power n is divisible by x plus y when n is odd. When n is odd. So when n is equal to 1, we have x plus y is equal to x plus y. And of course, x plus y is divisible by x plus y. And we have obvious representation, trivial representation. Next, odd number n is equal to n 3. So we have x to the power 3 plus y to the power 3 is equal to x plus y times another polynomial, which is written as x to the power 2 this polynomial has degree 2. A next element will be x to the power 1 and y. So we decreasing the power of x and increasing power of y. Here we had y to the power 0, but we didn't write it. Next, we increasing power of x. We have, decreasing the power of x. We have x to the power 0 or 1. We do not write it. And increasing the power of y. And we put always, first we write minus and then plus. So we have minus and plus. Let's write for next odd number n is equal to 5. We have x to the power 5 plus y to the power 5 is equal to x plus y. Here we have x to the power 4. Next we write x to the power 3y, x to the power 2y squared, x y to the power 3, and last one is y to the power 4. We write minus, plus, minus, and plus. So it was formulas for n1, 3, and 5. And let's do not write for n equal to 7. This is done along the same way. Next case is divisibility of x to the power n minus y to the power n is divisible by x plus x plus y when n is even. The first even number n is equal to n to the n2. So we have x to the power 2 minus y to the power 2. It can be represented as x plus y times x minus y. So this is divisible by x plus y. Next even number is n 4. So we have x to the power 4 minus y to the power 4. It can be represented as x plus y times another polynomial of degree 3. This is x to the power 3, x squared y, x y squared, y to the power 3. And we write first minus, then plus, then minus. For n, next even number n, which is 6, we write x to the power 6 minus y to the power 6 is equal to x plus y times x to the power 5, x to the power 4y, x to the power 3 y squared, x to the power 2 y to the power 3, x and y to the power 4, and y to the power 5. We write here minus, plus, minus, plus, and minus. And that's all. Next case, when x to the power n minus y to the power n is divisible by x minus y, not plus y, but minus y. In this case, we have divisibility for any n. So for n, 1, we have x minus y is equal to x minus y, and x minus y is divisible by x minus y. Trivial case. Next, when n is equal to 2, we have x squared minus y squared. Again, this is equal to x minus y times x plus y. And this is divisible by x minus y. and we have this representation. Next, n is equal to 3, so we have x to the power 3 minus y to the power 3 is equal to x minus y times polynomial of power 2, x squared, x, y, and y squared. We have to write here plus. By the way, obviously, you know this from previous tutorials, this polynomial can be found when we divide this polynomial by this polynomial. And how to divide polynomials, watch our previous tutorials again. When n is equal to 4, we have x to the power 4 minus y to the power 4 is equal to x minus y and times another polynomial of degree 3, which is written as x to the power 3, x squared y, x, y squared, and y to the power 3. We write plus. We always write plus in this case. And the last case, when n is equal to 5, x to the power 5 minus y to the power 5 is equal to x minus y, and another polynomial of degree 4, x4, x3y, x squared, y squared, x, y cubed, and y to the power 4. And we write always plus. This was everything for this tutorial. Like us and subscribe, and thank you very much for your attention. In this math video tutorial, we will learn polynomials factorization. Using factorization of polynomials, we can transform complicated algebraic expressions into simple expressions. And sometimes polynomial can be represented in the form of a product of two or more polynomials or monomials. This is not always possible and often very difficult to find the required factors. And what gives us factorization? It permits simplify expressions. For example, when we have common factors in numerator and denominator, we can cancel out factors in numerator and denominator. Let's give a basic factorization techniques. If all terms of the polynomial contains the same expression as a factor, we can take this common expression out of brackets. For example, assume we have a polynomial 6b squared xz minus 12 b to the power 4 x squared. We can take 6b squared and x out of this polynomial, and we will have z minus 2b squared and x and x. That's why we represented our polynomial as a multiplication of a monomial and another polynomial. That's why we can, if we had, for example, an expression, something like this, minus 2b squared x. In this case, we could cancel these two polynomials and have an answer 6b squared x. That's why factorization of polynomial is very important. And this technique is quite complicated. Another example, assume we have 8 x cubed y squared minus 2a x squared y plus 4xy. And we can take 2 out of these three numbers, 2, and we can take out x out of these three factors, x. What about y? We can take out y out of these factors, and we will have 4x squared y minus ax plus 2. So again, we this polynomial, we represented this polynomial as this monomial times this another polynomial. Sometimes it's possible to break the terms of the polynomial into groups and find the same expression in all sets of brackets and factor out this expression. For example, assume we have cy plus dy plus cx plus dx. In this case, we can take this y out, and we will have y times c plus d, plus here we will take this x out, and we will have x times c plus d, and next we will take out this c plus d inside brackets, and we will have c plus d times y plus x. So let's repeat it again. Sometimes it's possible to break the terms of the polynomial into groups. And find the same expression in all sets of brackets and factor out this expression. We was talking about this expression c plus d. So factoring can be quite complicated, and you need practice to understand how to do this in real life when solving problems. Another example, assume we have 10 x to the power 3 minus 6 y to the power 3 plus 4x y squared minus 15 x squared y. We can take out for these two terms of our polynomial 5x squared, and we will have 2x minus 3y. For these two terms, we will take out 2y squared, and we will have 3y minus 2x. Here we can write, since, as you already noted, this term and this term are equal except the sign, so we can change the sign for second term of our expression and write this will be equal plus 2 y squared, 2x minus 3y. And next we will take out these two factors out of our expression, and we will have 2x minus 3y times 5x squared plus 2y squared. So we have 6ax minus 2bx plus 9by and minus 27ay. We can take out 2x, and for these two terms, and we will have 3a minus b. Next, for these two terms, let's take out 9y, and we will have b minus 3a. And now we rewrite, and as in previous example, change the sign of second term, and we will have minus 9y, 3a minus b. Next, we take out these factors, and we will have 3a minus b times 2x minus 9y. In next example, sometimes we need to add new terms to perform factorization. Let's assume our famous case, our famous example, a squared minus x squared. As we know from previous tutorials, this is equal to a minus x times a plus x. And to perform factorization, we subtract ax and again add ax. And next, when we take out a, we will have a minus x. Here we take out x and we will have a minus x. Next, when we take out these two brackets, we will have a minus x times a plus x. That's all. And next example, a squared plus ab minus 2b squared. This example, a little bit, it's not, I cannot say this is easy, it's not hard, but you have to practice to perform next factorization. Here, we write this as AB. AB is written as plus 2AB minus AB. And this is equal to AB. So we rewrite our AB as 2AB minus AB. And let's rewrite minus 2b squared. For these two terms, we take out a and we have a minus 2b. For these two terms, let's take out minus b and we will have a minus 2b. Next, we notice that we have same two factors, and when we take out a minus 2b, we have a minus b. So all in all, we transformed our polynomial into, we performed factorization and transformed our polynomial as a multiplication of two monomials or two polynomials. Sometimes we have to use shortcut multiplication formulas we learned earlier. Let's write it again. Shortcut multiplication formulas are used in algebra again and again, and we can write it as in previous tutorials. As we know, this is equal to a plus b squared. If you don't understand, watch our previous tutorials. This is quite easy examples. And next example, a squared minus 2ab plus b squared is equal to a minus b squared. A squared minus b squared is equal to a minus b times a plus b, as we know from previous example and from previous tutorials. Using these formulas, we can solve this example. For example, if we have 4a squared plus 20ab plus 25b squared, and using this formula, we can write it as 2a plus 5b squared, because when we use this previous formula, we can write these brackets squared as 4a squared plus 2 times 2a and 5b, it will be 20ab plus 5b squared, which is 25b squared. That's all. And factorization of polynomials is quite technical, as I said. This is technical work, and you have to practice this technique. Next example, assume we have 12 plus a cubed minus 4a minus 3a squared. We can write this as 12 minus 3a squared minus 4a plus a cubed. And if we take out, for these two terms of our polynomial, if we take out 3, we will have 4 minus a squared. For these two terms, if we take out minus a, we will have 4 minus a squared. And we have two common factors, and if we take out this 4 minus a squared, we will have this multiplied by 3 minus a. So as we see from this example, you have to practice factorization techniques a lot to represent polynomial as a multiplication of different monomials and polynomials. And this is very important for transforming complex algebraic expression into simple algebraic expression. Like us and subscribe. It was everything for this tutorial. Thank you very much for your time. In this math video tutorial, we will learn algebraic fractions. Let's get started. Don't forget, like us and subscribe. First of all, let's begin with a definition and understanding of algebraic fractions. An algebraic fraction is an expression of the form a divided by b. where a and b are monomials or polynomials or polynomials. As we know, monomials is polynomial with one member. For example, this is a monomial, but for example, if we have plus z, this is already a polynomial. In this case, in our algebraic fraction, a is called a numerator and b is called a denominator of our algebraic fraction. And rules for arithmetical operations of algebraic fractions are the same as for simple fractions, and we will give review of basic operations. So if you don't understand what is a fraction, you have to watch our arithmetic playlist in this channel, Open Math Camp. Let's give examples. Example of reducing algebraic fractions, AF, shortly. Assume we have 18x squared y to the power 5 divided by 21x y to the power 3. This fraction can be reduced, and this is done by assume, first of all, watch at these two numbers. Since this fraction can be represented as 18 over 21 times x squared over x times y to the power 5 times y to the power 3. And that's why each of these elements of our fraction must be cancelled out correspondingly. That's why, first of all, we watch at this first element. And since 18 can be represented as 3 times 6, and 21 is represented as 3 times 7, and this 3 and 3 is cancelled out, so we have 6 over 7. From this x, we have cancellation of x and cancellation of these two. So x squared divided by x is x, and we write here x. And from this y, we have cancellation of this y cubed, and from this 5, we will have y squared. And this is final answer after reducing our fraction. Next example, assume we have 100 a to the power 3 b to the power 5 divided by 120 a to the power 5 and b to the power 3. In this case, our 100 and 120 can be divided by 20, and we will have 5 over 6. And from these two elements, we have at the denominator a squared. And if we look at this b to the power 5 divided by b to the power 3, we will have b squared in numerator. That's all. As we already noted in previous tutorial, the factorization is very important when we want reduce our fraction. Let's give an example of reducing fraction after factorization of numerator and denominator. Assume we have a fraction a squared minus 2ab plus b squared divided by a minus b. Using shortcut multiplication formulas we gave earlier in our playlist, algebra playlist, we know that this polynomial in numerator can be written as a minus b squared, and divided by a minus b, this is equal to a minus b, and that's all. So we transformed our complex algebraic expression into simple one. Next example, assume we have a cubed minus b cubed divided by a minus b. Once again, using shortcut multiplication formulas, a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared, and divided by a minus b, after cancellation, this is equal to a squared plus ab plus b squared. Next example, more complex example. Assume we want perform reducing of this fraction to a squared minus ab minus 3b squared divided by 2a squared minus 5ab plus 3b squared. Let's denote this as a over b. And next, let's perform factorization of polynomial a. If you rewrite it, this is 2a squared minus ab minus 3b squared. And we can write it as 2a squared minus 3ab plus 2ab minus 3b squared. What we did here, obviously this minus ab is equal to minus 3ab plus 2ab. Next, we write these two terms as a times 2a minus 3b. And these two terms can be written as b times 2a minus 3b. And that's why our polynomial a can be written as 2a minus 3b times a plus b. So we finished with numerator of our fraction. Let's begin with denominator of our fraction. Along the same way, our denominator can be written as a times 2a minus 3b minus b times 2a minus 3b. And this is equal to 2a minus 3b times a minus b. And now we for a and b, we know how a and b can be factorized. And after factorization, let's rewrite this again, and it will be a divided by b, where a is 2a minus 3b times a plus b over 2a minus 3b times a minus b. Next, we perform cancellation, and at last we will have a plus b divided by a minus b. And that's all. So all in all, after reducing our complicated algebraic fraction, we have a simple form of our fraction.